I'm Tung Lee. This is a joint work with Huang, Yavuz, Shi, and Huang. So nowadays, storage as a service has become more and more ubiquitous. It can provide a sophisticated data storage facility and infrastructure for clients to outsource their data to the cloud. This can reduce expensive data management, maintenance, and archival costs. However, cloud storage also brings significant concerns regarding data integrity to the client. Data loss can happen due to unwanted accidents such as hardware failures or adversarial behaviors. For example, the adversary may delete certain parts of data that are rarely accessed to reduce storage overhead and monetary costs. As a baseline design, the client can compute hash mark of her data and enclose hash mark with data on the cloud. Then later, the client can download her data to verify with hash mark to check the integrity of outsourced data. However, this incurs a lot of overhead to check for a large database. Proof of retrievability proposed by Yavuz and Kaliski in 2007 enables the client to store data blocks with a cloud server so that later the server can prove the possession of all data in a very efficient manner. Its mechanism is to insert sentinels into random position in the database. For each audit request later, a portion of the inserted sentinels are used to verify. This first POR design is static, which means it doesn't support update. And the number of audit times is limited. Proof of retrievability works as follows. First, the client sends an audit request to the cloud server. Then, the server returns the audit proof back to the client. By verifying this proof, the client can ensure her outsourced data is still kept intact. To support both update and audit, dynamic POR schemes have been proposed. Previous works focused on designing DPORs that achieve low storage, fast update, and metadata privacy. Our DPOR design, which is copolar, aims to achieve small proof size and low audit time. Now I'm going to talk about our polar design. Based on previous work by Shi et al. In 2013, our polar also performs encoding data by a type of error correction code. Basically, error correction code allows recovering the entire dataset while tolerating a certain portion of damaged codewords. The error correction code that we use can allow up to half of codewords to be corrupted. The codeword is computed as a formula here. A permuted data vector multiplies with a matrix G. The output codeword here will be double longer than the original data. So because any square submatrix of G is not singular, we can compute the inversion of the submatrix of G and multiply it with a corresponding subset of codewords H, denoted as H hat here to recover the original data. For more details, please refer to our paper. We also have MATLAB example code here to exemplify how to build this error correction code and how to use it to recover data. The database that our polar stores includes three components. Raw data buffer U. Erasure code C is error correction code computed from data buffer U. Hierarchical log H is incrementally constructible code, where level L contains the codewords of 2 power L newest updated data block. For example, an updated data block will be written to H0, and after another new block, H0 will be cleared, and H1 will be rebuilt. And continue, after the next two new blocks, H0 and H1 will be cleared, and H2 will be rebuilt. Similar for the next level, H3. So level HL is rebuilt after 2 power L updates happen. And after n updates, where n is the total number of data blocks, the erasure code C will be rebuilt, and codewords in H at every level will be cleared. In terms of amortized cost, each update just requires a computation complexity of big O log n, where n is the total number of data blocks. And ICC operations are based on MFT butterfly circuit. I'm going to introduce several definitions and notations in our work here. We use alpha to denote a secret key. A data block V is written as a vector of values. The commitment of a data block is Cm, with G is a vector of group elements. And mark of commitment sigma, which is computed with secret key alpha, and another component H power R, with H here is a group element, and R is the output from a pseudo-random function with another secret key K. This mark has the important property that it is additively homomorphic, which means we can compute the mark of a linear combination of data blocks from the mark of separate components. You can have a look at our paper to see the proof of its homomorphism. As described previously, our data structure includes a raw buffer U, which is integrated with Merkle tree. The client keeps track of the root of the Merkle tree to verify the integrity of data when reading from raw buffer U. Hierarchical log C is computed from raw data buffer U, and hierarchical log H. And each code word block in erasure code C and H is enclosed with a homomorphic mark. To update a data block, the client writes it to the raw buffer U. In addition, the client also needs to update hash mark value on the Merkle path corresponding to the updated data block. And the root of the Merkle tree is kept by the client to check the integrity of data when reading from this raw buffer later. The client also sends a mark tag of the updated data block, and the server uses the data block and this tag to perform updating hierarchical log H. When rebuilding a level in hierarchical log, the server receives complementary values from the client to update mark tags as a new level. And after n updates, where n is the total number of data blocks, erasure code C is rebuilt from raw buffer U. So our audit procedure works as follows. In erasure code C and each level of hierarchical log H, we choose lambda random code words and their markup commitments. Then we compute the aggregated code words and its map value, sigma, as the formulas shown here. Rho Li here are random scalars indicated by the client. These scalars value can be generated from a random seed value. We can consider this as a random linear combination of code words and its homomorphic mark. So our audit protocol suppose that a user stores his database on a cloud server and would like to perform an audit. The client starts by sending an audit request and a random seed to the server. Then the server returns back to the client the commitment and markups the aggregated code word block. The client with secret key alpha can compute mark from the commitment of the aggregated code word and compare it with the aggregated marks that they received from the server. If they are equal, it means the commitments of data blocks are correct. However, the server can compute the commitments of code word blocks and just stores the commitments and map values of code word blocks. So code word blocks can still be deleted from the server and the audit protocol is still passed. Therefore, audit proof created by using only commitment and markup the aggregated code word block is insufficient. The server needs to provide a proof of its knowledge about the aggregated code word block for the client. So following the description before, the server now needs to send a proof of its knowledge about the aggregated code word block. And the client verifies this proof to be certain that the server stores real data blocks. The proof can be the aggregated block itself. However, if the data block is large, then the proof size is also large. So to reduce the proof size, we harness two verifiable computation techniques. The first one is inner product argument in bullet proofs, and the second one is KZG. Bullet proofs doesn't require trusted setup, while KZG requires trusted setup. The proof size of using inner product argument in bullet proofs is big O log D, where D is the data block size, and the proof size of KZG is a constant. The idea of using verifiable computation techniques to create a proof of the server's knowledge about the aggregated code word given its commitment P is as follows. We let the client send an evaluation point X to the server. Then the server uses two mention techniques in a product argument implicit proofs and KZG to create proof that it knows the aggregated code word, satisfying the given commitment P as a dot product between the aggregated code word and vector X, which is a power series from the value X here. Then the server sends the proof back to the client for verification. And this is the size of using two schemes. Our parallel using inner product argument implicit proofs creates a proof of size 2 log D plus 2 group elements and 2 elements in ZP. And our parallel using KZG creates a proof of 3 group elements. To evaluate our parallel, we use an Amazon EC2 instance with 16-core Intel Xeon and 64GB RAM. Our client is a laptop i7 with 16GB RAM. Our implementation is in C++. We use SECP256K1 library for our parallel scheme with inner product argument and BN254 for our parallel scheme with KZG. We perform comparisons with remarkable and state-of-the-art deep QR designs. Regarding the proof size, the audit proof size of parallel, it is 87 to more than 14,000 times smaller than prior approaches. The proof size of parallel using inner product argument depends on the block size, but for both our parallel schemes, the proof size is small and independent with database size. About end-to-end audit latency, our parallel is 4 to 18,000 times faster than prior approaches. The trade-off of our scheme for smaller proof size and small audit time is the update latency. It's the longer update latency in comparison with previous deep QR design by Seattle in 2013 using the same erasure code. Our update is 1.2 to 3 times slower. Additionally, we also present how to modify the protocol to implement public audit mechanism in our paper. In conclusion, our parallel design is a dynamic PR scheme that achieves small proof size and low audit end-to-end latency. In addition, it also maintains a reasonable database performance. We publish our source code here. Please visit it for more information. This is the end of my presentation. Thank you for your attention. I would be happy to answer any questions.
How did you evaluate the practicability of this?
Any performance?
Yes. No, not in the lab, but do you have any connection to any cloud provider?
We only use Amazon EC2 instead. We do not use any server that are from the university or our lab. Yep.
Okay. And you also evaluate attacks on it? Possible attacks?
Possible attacks?
Yeah.
I think, we have a proof about that where they are more that greater than or equal to half of Google blocks to be drafted, then the probability that the update path will be negligible.